Alright, so let's talk about reflection. So we're going to take a rectangle and we're going to reflect it over over the line of reflection. So this is the line of reflection. It can be anywhere. It can be up and down. It can be laying down. It can be across. It can be straight in the middle of your graph. It can be off to like the side. Your line of reflection can be anywhere. I apologize for the fact that it says reflection, but later on I have stuff here and stuff down here, so I have to look like that. So here is my pre-image. This is a beginning picture that I'm going to have. And I want to reflect it over this line of reflection. So consider the line of reflection kind of like a mirror. So if I'm looking at the mirror, it would break. No, I'm just kidding. If I'm looking at a mirror, then on the other side, what should I find? Well, on the other side, I should find myself. So this would be your regular image. So if I continue that, if I have my image on this side, and I want to reflect it over to the left, it would just do the exact same thing. All right? So the line of reflection just lets me know where all these guys are going. And this point to the line is the same distance as the line to the next point. All right, so each point, so like if I'm talking about this point right here, and I count all the way to the line, or I use a ruler or something, it would be the same distance as if I took the line and went all the way to the other corner. All right, so it does make a difference. You can't just randomly put it somewhere on the other side. It has to be the same distance from each corner to the line. All right, copy that down. I'm going to turn it in 5, 4, 3, 2, 1. So this means that even reflections such as the second, fourth, or sixth will map the image back to the pre-image along the same line of reflection. We can use the same procedure for other quadrilaterals like a parallelogram, trapezoid. It can be done on pretty much any type of figure. So reflections along specific mirror lines on some symmetric plane figure maps the image onto the pre-image. For example, in a rectangle, reflections along the dotted mirror line will result in the image being mapped onto the pre-image. So none of this stuff needs to be copied down. So I would copy down this graph right here, or this figure. The rectangle is mapped onto itself along the mirror line. So if I look at line 1, so if I look at line 1, and I would fold this rectangle down the dotted line, what would happen? What would happen, guys? That's right. If I fold it down this side, it just folds it in exact halves. So this side on the left is the same as this side on the right. Now, if I fold it down the L2, so line 2, and I fold it hot dog way, we get the exact same thing. The top side is going to be the same as the bottom side. Pause it if you haven't copied on the figure. You don't really have to copy down the words up here, just a figure. All right, so rectangle MNOP is mapped onto itself when reflected along the mirror L2, as shown below. The vertices of the image have the prime symbols. So if I fold this rectangle down this dotted line, this M is now down here where the N is at. That's the reason why it has the little prime symbol. This N now switches with the M, so that's why it's N with the little prime symbol. P goes down here with O, so prime symbol. and O goes with P, again, prime symbol. Once you move something, that's when you have the little prime symbol. The little figure, that's called a prime symbol. Copy it down. I might write this down just so that I remember why these things show up. 3, 2, 1. So an isosceles trapezoid and rhombus are mapped onto themselves when reflected through the dotted mirror line shown below. So this is a trapezoid. Here is a rhombus. So if I want to know, when it says mirror lines, reflected through, mapped onto itself, there we go, mapped onto itself, it means I need to, if I fold it down this line, this side right here is the same as this side right here. I can't, if I cut it here, both sides aren't the same. If I cut it diagonally, both sides are still not the same. So it won't work. It only works down this section right here, down the middle. All right? For a rhombus, it only works down the diagonals. So if I want to be able, so this side and this side are the same, and if I fold it the other way, and, obviously make a horrible straight line, I would get the exact same thing. So I'm just trying to find out where I can fold it, where it's this point and this point will match together. It'll be a perfect fold. For rectangular polygons, the lines of reflection that map the image back to the object are equal to the number of sides of the polygon. For instance, in a regular pentagon, there are 5 lines of reflections that will map the polygon onto itself. And we're only talking about regular polygons. So depending on how many sides it has, 1, 2, 3, 4, 5, I should be able to find 5 lines where if I fold it in half down that line, it would land on each other. So if I fold it here, both of these 2 sides are the same. If I fold it down here, this side here and this side here would be the same. If I fold it here, this side on the top and this side on the bottom would be the same. This side would be the same and this side would be the same. These 2 halves would be the same. Oops, sorry. All right, so I would really copy this whole section down and write this down. So write this whole page down. Pause the video. Turning in 3, 2, 1. So let's see if you guys can figure this out in yourselves. If you don't want to do this, then you don't have to. You guys can just move on to your worksheet. So find the least angle of rotation that a regular pentagon can be rotated about its center to get mapped onto itself. So when I'm trying to find out the rotation angle, that means I'm using that 360 degrees divided by the number of sides. So I would do 360 all divided by how many sides does it have? Pentagon, what does it say on here? It's 5. Alright, so we're going to put a 5 equals, and you can put that in your calculator and you'll get that the answer is 72. Alright guys, so from here you guys are going to pull up day 7 worksheets and work from there. Again, you'll be going to day 7. If you have any questions, please let me know. Have a good day, guys.